In this video tutorial, we'll be looking at buckling of a column, a slender column, using a nonlinear method. We'll again start our analysis with a simple static solution. So we still are going to use the beam 188 element, beam 188, and then we wanted to use a quadratic form of that, and that element will have a cross section of beam type, which is a rectangle, and dimensions 10 by 20 millimeters. Apply, preview, and OK on that. And in terms of material properties, it's going to be linear elastic materials, but we'll have geometric nonlinearities, large deformations active. That will make the modeling in this case nonlinear. So structural, linear elastic, isotropic, 200,000 for Poisson's ratio 0.3, 200,000 for the Young's modulus, and 0.3 for the Poisson's ratio. Okay, we can close that. So we'll create our key points in the active coordinate system. First key point at the global coordinate system, 0, 0, 0 coordinates, and the second key point at 1000 millimeters in the y direction. And we can create a line, a straight line between these two key points, and that is all the geometry that we'll need to create for meshing this with beam elements. We can use the attributes for these lines, and that's going to use material 1, element type beam 188, section 1. And in this case I'm going to leave the orientation key point as default. We can now do the meshing. First, mesh tool, and specify number of divisions on this line, and we wanted 10 elements through the length. Okay, and raise hidden and mesh the lines. Okay, and we also can show the true size and shape of these elements using the /e shape command or through the menu option. So we can confirm that the cross section is rectangular as we intended. We can now go to solution, and new analysis type is static. That is fine. We can check unabridged menu and go to analysis options and make sure this pre-stress effects is turned on. Okay, that. And we can then define our loads. Displacement is simply fixing the bottom key point in all degrees of freedom, and a force at the top key point in negative y direction. So Fy is -1. I'm repeating the linear elastic, linear buckling initially, because I'll use that result for updating geometry. The static analysis, solve the current load step, that's fine, close that, and under general post-processor we can look at the deformed shape, which is as we have got before. Now I can go back to my solution and change my analysis type to eigenbuckling, and my analysis options, I can say specify 2 modes to extract, and another one to take here, as we mentioned before, was under load step options and expansion pass, single expand modes, and to be able to click this button for calculating the element results, and number of modes to expand was 2 as well. And now if we do the solution, that will give us our eigenvalue, and eigenvector results. So let's check them. Under general post-processor, result summary is the linear results again, and read results first set, plot results, deformed shape, and that's my first mode. And read results next set, plot results, deformed shape, that's my second mode of buckling. Now what we can do is use these linear buckling mode shapes to update the geometry for the nonlinear analysis. There are a couple of different ways of starting a buckling process within a nonlinear analysis. One would be to apply a perturbation, for example by applying a small force that is going to force the beam in the transverse direction, and the other one would be creating a shape imperfection. And the convenient way of creating the shape imperfection is by updating the geometry based on these buckled mode shapes. So we can try the first method. We'll need to go back to solution and create a new analysis. This time it's going to be static, and OK. And under solution controls, we can specify what is the time at the end of the load step. I know that for this beam, the maximum load I can actually expect is not going to be much greater than 830 newtons or something like that, because that's my critical buckling load. But I can try to put a load step at 1000 seconds, and I can specify my time increments as say 1 second, or as a minimum 1 second, maximum 10 seconds, and probably choosing 5 for my time step would be fine. And what I can do then is look at other options. That's the solutions options for equation solvers. We don't need a restart, and there are nonlinear options here as well, and these are program chosen, and we can leave them as they are. Advanced nonlinear, again there are arc length options, for example, or stabilization options, which will help with some of the more difficult problems that will have problems converging. So if we can now look at the basic solution, one of the analysis options here is assuming small displacement static, but I know that this is going to be a nonlinear problem because of the large displacements, so I need to turn on large displacement static, and that is fine. Another important parameter that we'll need to specify is the db results file frequency of writing the results output. So that is under solution, load step options, output controls, db results file. So we want to write the results at every substep, otherwise the default is to write the results at the last substep. So if we OK that, we can now start the solution. So solve, current load step, and OK. And the solution will be done for 1000 seconds from start to finish, and that's completed very quickly because these are just 10 simple beam elements. So we can now go to the general post processor and look at the results summary. So we can see that there is a set of results written from 5 seconds, our starting time, up to 1000 seconds. So we can look at say the first set, plot results, deformed shape, that's fine. Deformation is very small, and our interest is how does that deformation change in time. So we can go to do an animation of results over time. So we want to see, for example, in 100 frames on a time range going from 0 to 1000 seconds, and animation time delay, let's say 0.1, and let's say we want to plot the displacements in the x direction. Okay, so we can see how the deformation is progressing on our buckled structure. So the time is also corresponding to load. As load approaches 800 newtons, our beam starts to deform significantly. So we can stop that and close, and we can again read results by pick, and we can pick a result from near the buckling load that we were predicting. Let's say 827. Read that, close, and then plot results. We can plot the stresses at that point. So that would be the, say, stress in the x direction for the beam elements, and we can see that this is at that point deformed 50 millimeters, and maximum stress there is at the base, which is about 122 megapascals in the beam bending direction. So that is for a load of 827 newtons at the top of the beam, and at the time 827 at the same time. So these are the nonlinear results, and we can do another interesting plot, but this time using the time history post-processor. We can pick for example the results in the x direction from a certain node. Let's pick a node at the top of this beam, and then that's going to plot the x displacement throughout the time history. So let's say plot that, and just take the window out of the way. Just close that otherwise. We can see that as the time progresses to just over 800, the large deformations start, and the beam starts to actually buckle at that point, and then these result in very large deformations. If we can look at the last set of results, we go back to general post-processor, we can read the results by last set, so that's at 1000 seconds and 1000 newtons applied at the top. So if you plot the results, nodal solution, and the x component of stress, we can see that the deformation is very large, 751 millimeters, and the stresses calculated for that are also very large. So at the bottom of the beam we are getting almost 2000 megapascal stress. That is actually not realistic, since we have assumed linear elastic material properties. The beam is still able to carry some load at this very large deformed state, but in the next session we'll be looking at elastic and plastic material properties, and the beam made of something like steel, if it is, say, low carbon steel, then yield strength 300 megapascals, that sort of stress will simply take it to the plastic range. So the stress typically shouldn't exceed 300 megapascals, and it will go plastic after that. So this is a graphical interface driven way of looking at the nonlinear analysis. However, as I shown in the linear analysis, creating a notepad command structure for this is just as convenient to create your nonlinear analysis, and it's then pretty straightforward to copy and paste from your command log file into ANSYS window. So in this case, in the first part, I'm doing a static analysis, and then this is the static solution, and this part is doing the linear buckling. And in the nonlinear buckling, there is two options here. Either updating the geometry, as I mentioned, from buckled mode shapes, and the other option is creating a perturbation force. So in this problem, we had a perturbation force of just simple 1 Newton in the x direction. So we can run this log file, and this time run it for updating the geometry. So this upgeom command will look at the first mode shape and scale the results by 1, and then this will all be read from the file.rst results file that was written at the end of the linear buckling. So the nodes will be updated by the deformed shape, the eigenvectors of this buckling analysis, and that will create a small imperfection, and depending on the scale value you can create more or less perturbation. So let's try to run this based on this analysis. So I'll clear the model and run my static and linear buckling analysis in a simple step. So the solution is done, and the next part is in the prep 7, updating the geometry. So that has created a small imperfection on nodes based on the eigenvectors of the buckled mode shape. And then in the next part, I'm specifying the solution options. Again, it's going to be a static solution, but nonlinear geometry effects are going to be on. I can specify a number of equilibrium iterations and print and results outputs at every sub-step. Automatic time stepping will be on with a delta time of 5 seconds, minimum 1 and maximum 10 seconds, and fixing the bottom and then applying my perturbation load. And I've specified a critical load here as well as a parameter, minus 822, and what I've done is specifying a critical factor. For example, 1.02 multiplying 822 is applied in this time step, and then solved, and then increased the load level and updated the time, and then solved again and increased the load again here, and then solved for that increased time value. So this is done up to a certain value of load, in this case maximum 1.3 times my critical load. And next bit is to display my results and also creating the XY plot of load displacement. So let's run the solution for these different load steps that I've created. This is pretty difficult to set up interactively, so a log file is really essential for making number of load steps using mechanical APDL. So that has solved up to a level of 1068 seconds, and remember my load level is effectively the same as my time, so it has managed to converge even at a load of 1068 newtons. So if I bring up my log file again, I can take a result from a particular time, for example 800 seconds, and plot displacements on that. So I can find that this is displacing 55 millimeters as predicted in the previous run. And the other interesting bit is to create a load displacement plot. So I can do this using commands as well. I can see that just around 800 newtons the column is starting to buckle, but still able to carry a load for very large displacements, simply because we assumed the material is linear elastic. However, in the next videos we'll see that by creating an elastic plastic material property, we'll actually collapse this structure.